Hassan? It's there. Hello?
Okay. There. Coming up in a bit from UTRC, from the United Technology Research Center in Ireland, and they will talk with us about the integration of models to evaluate the performance of retrofitting scenarios.
Thank you very much. Thank you very much. Thanks all for coming. Basically, my talk is mostly about simulation. And actually, I want first to thank my colleagues in OptEEmAL and our partners, because actually it was a real challenge for me and all the members of our team to produce automatically thermal simulation models from BIM files. So why we need building simulation models? Because we need to assess retrofit scenarios in OptEEmAL. So in order to do that, we have to develop a series of tools acting as in a tool chain that ensure that the final building simulation models will be correct and appropriate for in terms of OptEEmAL. So my talk is mostly about these developed tools. So as I said, and we need these models, simulation models, to assess retrofit scenarios. Then we have to, after we use external tools, simulation tools, to perform the simulations, compute the district performance indicators, and then communicate back and export using the platform these district performance indicators. In order to produce appropriate simulation models, we have to pass through three stages. One is related to the data preparation. The second one is related to the data checking. And the last one involves transformations in order to produce these simulation models. So I will walk you through these three stages. So where in OptEEmAL we need building simulations? We need basically into two stages. One stage is the initial stage where we assess the baseline, the building in the baseline stage, where as they are. And then after the also during the optimization, where we apply the retrofit measures, and we need also building simulations in order to assess the retrofit measures, called energy conservation measures. So this is the overall picture of the project, and basically the scenarios generate on the simulation. The part that I'm going to talk about is this certain, basically inside this central green box. So as I said, we have these three stages. And the initial data preparation stage involves a series of guidelines that we give to the designer in order to make sure that the building designs are appropriate, and also involves some required modifications in the existing exporters, IFC exporters. We use IFC, as I forgot to mention, as our building schema, data schema, and we do it because it's a domain agnostic schema, and also promotes interoperability among different disciplines. So, we have to modify some exporters in order to make sure that the amount of information is appropriate in terms of OptEEmAL that exists in IFC. And then, in the second stage, we have a stage when we do a semantic enrichment. We use a series of tools in order to enrich the models, the simulation models we generate, and make sure with the data appropriate for OptEEmAL. And the last stage is the DPI calculations, where we invoke the simulation tools and we perform the assessment via the calculation of distinct performance indicators. So in the data preparation stage, we give to the designers a set of rules formed as design guidelines, and includes things such as the correct placement of building spaces inside the building, the definition and the inclusion of material thermal properties, both for transparent and opaque constructions of the building, and also some parameters regarding the scheduling, the schedules of the referring to the occupants in the buildings, and things that are related, are required for the simulation as far as time scheduling is concerned. Then we have to also make sure that the existing IFC exporters export the information in the IFC files, the BIM files, the appropriate information. Right now, the existing exporters facing some issues. For example, they they export missing thermal properties, the schedules that are missing regarding the light, the occupancy, and also as it was mentioned previously, the space boundaries, which are the surfaces that thermal exchanges occur among building spaces, are missing. So we modified the exporters in order to cover within OptEEmAL, in order to cover these missing dependencies. So, and also this was as far as the data preparation stage was concerned. During the BIM checking stage and the data checking stage, we have developed two tools to do that. One is the BIM checking tool, which what it does, it makes sure that the information inside the IFC files is complete. There is no any missing material thermal property, or there is no any missing dependence among the thermal exchange surfaces called second level space boundaries. So this tool reports the results, the checking results in a text format. Another tool that we have developed is the so-called geometric error detection tool, which detects interconnections among building architectural elements. For example, here you see a class in interconnection among a building space and a building wall. So it reports these classes in a visual aid, also as well as a text output format. So the designer can improve the existing design by correcting these design errors. So, and also in the third stage are the semantic enrichment tools. So when we make sure we have an IFC file, a building information model data file that is complete and correct, we have to make sure it will have to pass through a transformation process in order to produce a simulation input data file. So for these reasons, we have developed another series of tools that performs this transformation. These are the CBIP tool, Dns Tool, and the C-model enrichment tool. And the IDF generation tool. So we'll walk you through the operations of these tools. So the CBIP tool, what it does, essentially, in very few words, transforms the architectural geometry of the building, the walls, the slabs, in a set of surfaces that through which thermal energy is exchanged among either the building spaces or the building spaces and the environment. That's it. So basically, for this, what you see here is the Turina Torre building. And what you see here is the basement. And you see, as you can see with the blue color, there's a set of surfaces. So these surfaces is essentially a partition of the ground slab into this set of surfaces. And each surface is among two spaces. So, for example, this one is among the basement space, and the first floor, one of the first floor spaces. So, we do this process for every building within OptEEmAL. And essentially, we produce this way the geometric component of thermal simulation models. And here on the right, you see also the same process applied on a building in Eibar district. We have another tool. So every building within OptEEmAL is connected, related to the environment. So the environment affects the thermal simulation of every building through the blockage of sunlight. So if there are surrounding buildings, we have a blockage of the sunlight. So this affects, and it has to be included. And this is actually the district effect of the building. In the district effect of the thermal simulations of the buildings. So we have developed a dedicated tool to include this effect called Dns Tool. What it does, it calculates the shading surfaces, a set of shading surfaces that affect through the whole year the building of interest. So for example, here on the left, you see this calculation for the Quadro de Marzo district. We selected one of the buildings, simulated buildings, the Turina Torre building. We get for this building, through the whole year, 91 surfaces out of 190 surfaces of the building that they affect by shading this building. Here, Eibar district is more complex. We have 198 buildings and only 220, we selected one central building to be simulated. And for this building, only 200 surfaces are affected by shading the building of interest. We developed this tool. This also helps us because if we know the shading, the specific surfaces that they affect the building of interest, we can achieve smaller simulation times because the execution time reduces, so we can run optimizations faster and without losing any accuracy. So all this data coming from the CBIP tool and the DNS tool have to be included inside the simulation models. So that's why, and also we use as an intermediate model before the final simulation models, the C model, which is an intermediate model that helps to gather all the information, the required data, in order to produce the final input data simulation models used for simulation tools such as Energy Plus, Nest. So this C model, so in this model we fuse all the geometric and non-geometric information that is required for simulations. And here, as you can see on the left, is what initially the C model has from the architectural component, and after the enrichment, you see on the right how C model is populated with the new required geometric information for building simulations. Now I will pass the floor to Hassan Ridouane, who will talk another important tool for OptEEmAL, which is called HVAC tool.
Great. Thanks, Georgios.
You're welcome, Hassan.
Yes. So good morning, everyone. So my name is Hassan Ridouane from United Technologies Research Center in Ireland. And I'm here to give you a quick overview of the simulation of the active systems within the OptEEmAL platform. So in OptEEmAL, all the active controls and renewables are simulated within a dedicated tool that was developed in OptEEmAL that is part of the simulation module. And we call it the HVAC tool, as you can see here. So the idea is to decouple the simulation of the active elements from the passive elements. And this way we have more flexibility on the type of system we want to model, the types of control strategies we want to implement, and so on. And here on the left, you see like an overview of how the tool, so this is the HVAC tool is here, how it's integrated within the platform. So on the top is the district data model that Gonzalo was describing earlier. And from there, we generate data models that go through a number of transformations to provide inputs on the one hand to the Energy Plus tool, as you can see here, and on the other hand, inputs to the HVAC tool in terms of system parameters, like equipment parameters, like efficiency, and so on. And along with that, so we use the output of Energy Plus tool to get an idea about the thermal demands, the temperature set points of the zones, and with that, we run the simulation and we calculate the indicators for the district. And looking deeper at the tool, so what does the tool have? So the tool is flexible to handle the district plant simulation, the building plant simulation, and also the zone level demand systems. As you can see, there are all the different types. You have baseboard, fan coil, and so on. And the tool has a library of models, equipment models covering boilers, heat pumps, renewables, different types of renewables, geothermal, PV, solar thermal, and so on. We also have models of demand systems and a set of control strategies, both applicable at the zone level and also at the plant level. And then the tool simulates, assembles the configuration that was recommended by the optimizer, simulates and calculates the energy and comfort indicators. Oops. Okay, so a little bit deeper looking at the architecture of the tool and how the inputs are being extracted from the data models. So we have, in the pink on the top, we have the data models and also the Energy Plus output file. And we have 3 dedicated parsers that extracts this data and make it available for the HVAC simulation in that box there. And these are what we call configuration files, text files with the parameters required to simulate the systems that were suggested by the optimizer for that specific scenario. So we will calculate the indicators for the baseline scenario and also for retrofit scenarios as well. Going a little bit more deeper into the components of the tool. As you can see here, so we have the input data, and this is the ones I mentioned earlier, the Energy Plus output, and also the data models for the equipment. And then from that, the tool will detect which system, the system type that's being suggested to be implemented. Is it going to be a boiler? Is it a heat pump? Which controls, and so on. And then the tool will take that information along with the output of Energy Plus to determine the size of the system. What size is the system need to be? And that usually gives us multiple solutions. Out of the library of the energy conservation measures we'll have multiple solutions that can meet the load of the district. And then we do the filtering. We eliminate the ones that are not applicable. Either they are oversized or we have other criteria to eliminate them. And then the output of this big block is the system that will be implemented at the district level or at the building level. And then in the controls, we will be selecting the best strategy that will be implemented to operate the system more efficiently. And then we do simulation in the bottom here, and then we calculate the KPIs. And the suggestion from the tool or the output of the tool will be the district performance indicators and also the systems that were selected, the decisions that were made by the tool. So for each building or for the district level, what system has been selected and what control strategy has been selected along with the indicators for that scenario. And here in this slide and the next slide will give you a flavor on the types of models that are implemented in the tool. So we have different types of boilers, natural gas, condensing and non-condensing, diesel boilers, biomass boilers, and these are modeled using nonlinear efficiency models. Similarly, we have heat pumps and chillers that are modeled as COP functions with the outside temperature and also with the part load ratio. Water loops, hot water loops, chilled water loops as well. So these are taking into account the circulation pumps, the water supply temperature, and also the return temperature into account. Similarly, so we have models for renewables, PV, and solar thermal are represented there, scheduling, controllers that act on the baseline schedule, they modify the schedule of the baseline, and then they calculate the new energy demands and so on. Then we have thermostatic valves that act on the supply temperature of the radiators to provide or to achieve the set points of the zone air. So these are just a few models. So we have models for all the systems that are in the Energy Conservation Measures catalog. I think Juan will talk about that a little bit later. And then this is my last slide. So it's an application of the tool functionalities to Cuatro de Marzo district that we have been discussing this morning. And looking at the baseline system, so we have 5 buildings in the district. And looking at the energy system, it's individual boilers supplying baseboards, a radiator system. And the tool will run different scenarios and simulate and calculate KPIs. And here I'm focusing on one specific scenario, just for the sake of presentation. And here we see the inputs to the tool. So these are the energy plus output for each building. We have 5 buildings, so each one is one output of energy plus for that building. And here we have the data models with the parameters, equipment parameters for each of those buildings. And then once we do the HVAC sizing and filtering, so we get the configurations or the systems that are suggested by the tool for each of these buildings. So we have building 4284. So we have a condensing boiler of size 03, and that's a specific size in the catalog. It will be like a 50 kilowatt boiler, for example. And you can see we have different types of boilers, biomass, condensing, non-condensing, and so on. We have also other systems, heat pumps, and so on. But for this specific case, it's mainly boilers suggested for each of the buildings. And the platform or the optimizer is also requesting that we implement renewables. So this is the full active control and renewable scenario per building. So there are also passive elements that are not included here. So we have renewables, we have PV for this building of this size, and also thermal collector of that size, and also that boiler. So this will be the system that will be implemented in this first building, and so on. And the tool will execute all that, and will calculate the district performance indicators, as you see a snapshot of that in the table. These are some indicative energy KPIs. Baseline compared to scenario 7, and you see reduction in the total energy consumption for that scenario. And you see the contribution of biomass, solar thermal, and so on. So, and as I mentioned earlier, so the tool will do multiple of these runs, and at the end will present the best scenarios for the district. So with that, I'll pass it back to Jorgos for just if you want to conclude sorry. Okay. You took your microphone.
Yeah, not a problem.
Great.
Can you hear me? I have a strong voice. Okay. Don't worry. So here after, so as we said, for OptEEmAL, it's very important to have these DPIs. So in order to calculate these DPIs, we have to generate the simulation models and calculate input, produce. Okay. Great. Oh. Okay. Okay, I will speak from a distance. Okay, so for every simulation, we need an input data file, an Energy Plus input data file to be generated, which is the file that is required for Energy Plus simulations. And this RALs is fed into a cluster of computing resources, and which are executed. So there are multiple executions in parallel in order to simulate multiple buildings at the same time. And then after these executions are concluded, the DPIs are calculated and are communicated back to the project repository. So this is one picture that is the left is about a demonstration building, a very simple building, and the right is a picture of Torre Turina, which is essentially what you see here is the geometric component of the requires input energy plus input data files. And as you can see, the building is all the building architectural elements and all the surfaces are partitioned according to the energy simulation needs. In order to calculate the thermal exchanges among building spaces, we need these partitions. And as you can see, every surfaces are, depending on their role into the thermal simulations, are characterized accordingly. Either there are slabs or roofs or parts among building spaces. All of them are characterized and are inserted into the input data file for Energy Plus. This process is whole automated. As long as there are no errors in our buildings coming either from the designer or the exporter, the rest of the process is automated. So, and these are all SketchUp figures that you see. All these files are fully automated, produced automatically. So here on the top, you see a concept diagram on how the DPIs, we have interdependencies among DPIs. For example, one DPI depends on other DPIs. So on the top, you see how these are interdependencies in the calculations of the DPIs are resolved. So you have, when you invoke the calculation, you have a request the dependent DPIs. And then using the tool, you apply a formula in order to compute the last DPI and communicate the last DPI back to the project repository. And on the bottom, you see an example where DPI energy 02, DPI energy 05 depends on DPI energy 02. So here we use Energy Plus as an invocation. We invoke Energy Plus for the calculation. We compute energy, we have computed energy 02, and then using the formula and the results of the Energy Plus, we compute energy 05. These are conclusions of this talk. We have developed a series of tools that supports the automatic generations of thermal simulation models. These can be also categorized classified into three categories. The first category is data preparation tools. The second category is data checking tools. And the last one is data enrichment tools. So all the enriched models, so we use a sim model as an intermediate simulation data format to support the simulation needs. So all we produce a sim model for every building, and then we enrich it with the required information for OptEEmAL. And then after that, we produce input data files for simulations, energy simulations, and calculate DPIs and communicate back the results to the project repository. Also, we can do HVAC. The HVACs are simulated via a dedicated tool that Hassan described, and which does sizing and equipment sizing, selection, and DPI calculation. Thank you very much.